Thank you so much for the introduction. I'd like to start by thanking QCware, QNASYS, and everyone who helped organize another great Q2B. And thanks all of you for attending this talk. I'm Sam Stanwyck. I work on quantum computing at NVIDIA. And today I'm going to be talking about the roadmap to quantum supercomputing and what NVIDIA is doing to help us get there. So at NVIDIA, what we build and what we've built for a long time are some of the world's most powerful computers and supercomputers, and the infrastructure and software to help them realize their full potential. So in the past couple decades, GPUs have gone from being almost exclusively used for gaming and graphics to powering almost all of the world's leading supercomputers and ubiquitous for solving our most important computational problems across scientific computing, AI, and HPC. And we see supercomputing and quantum computing as inextricably linked. Quantum computers will eventually work alongside supercomputers as accelerators, accelerating key kernels and enabling them to reach even further. And the supercomputers of today are actually essential tools for quantum computing research and getting to useful quantum computing faster. And this comes into play in a couple of areas. One is simulation. We all know that we need to develop better quantum algorithms. In the NISQ era, advantage is unclear, and there's a very wide parameter space to explore in quantum computing. And even for fault-tolerant algorithms, we need to improve on them, develop better algorithms, make them more efficient in order to realize a practical advantage over the best classical methods. And simulation is an essential tool for that because quantum hardware today can be limited in scale, performance, and availability. You can use simulation on the NVIDIA platform to go far beyond that in terms of scale, in terms of speed, and develop new algorithms at the scale of quantum advantage. The other important area is hybrid quantum classical computing or quantum accelerated computing. We know that quantum computers will not stand alone. They'll work together with CPUs and GPUs, classical supercomputers, each resource doing the part that it does well. In order to actually make that vision a reality, there's a lot of work to be done on both the software side and the hardware side. We need software tools to enable domain scientists to actually take advantage of quantum computers and to enable them to use them alongside the best tools for classical computing without bottlenecks. We also need innovation on the system side to tightly couple quantum and classical computers, enable quantum co-processing without delays, and actually enable classical supercomputers to help us get the most out of quantum computers. And at NVIDIA, we're working on all of this. And it's very important to us to partner broadly and enable the entire quantum ecosystem. So today we're working with a large number of groups across quantum hardware builders, quantum software and systems companies, companies that build simulation frameworks, enterprise end users, academic groups, and research centers. And it's been wonderful to see all of the talks at this conference that are where the NVIDIA platform is essential to the work, and we're always looking for new partners. And we're also always innovating with our fundamental platform. So last year, we introduced a new system called Grace Hopper, which combines our flagship Hopper GPUs with a brand new CPU called Grace, with unified memory and a very low latency interconnect. This year, we announced DGX Grace Hopper, which takes Grace Hopper and enables it to scale up to supercomputing scale, utilizing our NVLink and NVSwitch interconnect technology to make it all operate essentially as a single GPU. Grace Hopper, we expect to be transformative for AI and HPC, of course, but it's also going to be incredibly valuable for quantum computing research, development, and eventually deployment. And I'll talk about that a little more later on. So let's start with simulation. And let me introduce our SDK, which is called cuQuantum. So the way cuQuantum works is it sits beneath quantum computing frameworks you all know and love, and accelerates them on GPUs. So as a developer, you can use these frameworks, not have to make any code changes, and get access to the full performance of the NVIDIA platform. Q2 offers libraries for state vector simulation and tensor network simulation, enables simulation of ideal or noisy qubits, and enables simulation all the way from one GPU up to a full supercomputer. It's integrated into all leading frameworks. We make a Docker container available called the Q2 appliance, which provides a ready-to-deploy solution. And we actually have a new release of Q2 out this week, so make sure to check that out. As I mentioned, Q2, our mission is to accelerate the frameworks you all know and love, and we're very proud to have a great list of frameworks accelerated by Q2, now including Bracket from AWS, BlueCat, Cirq, Orchestra, PennyLane, Kibo, Qiskit, TensorFlow Quantum, XACC, and others. And we're always looking to add to this list and accelerate new frameworks. I don't have enough time to talk about all the exciting work that's being done with Q2, but I did want to highlight a few great results. One of them actually comes from here in Japan, where last fall, ABCI put on a quantum computing grand challenge. And for that grand challenge, they used Q2 to simulate quantum circuits on their supercomputer, and showed that you can go up to supercomputing scale quantum circuit simulation in seconds, where before it would take many minutes or even hours. This is kind of fundamental research work that's key to enabling the research community. If you can develop quantum algorithms and simulate them at scale in seconds instead of hours, it's a huge, huge benefit for productivity and innovation. The other work is in tensor network simulation. So if you're not familiar, tensor networks can avoid the kind of strict memory limitation that comes from state vector simulation, and often for lower depth circuits can enable scaling of the simulation to a very large number of qubits. So in this work, a team from NVIDIA research studied the max-cut problem, an NP-hard graph optimization problem, often studied in quantum computing, and they developed a new variational quantum algorithm to solve max-cut. And using Q2, the tensor network library, they were able to simulate an accurate solution to max-cut for 256 qubits on a single GPU, and then on 20 DGX A100 nodes, so 160 A100 GPUs, they were able to get an accurate simulation of a problem with 5,000 qubits. So this was multiple orders of magnitude greater than what had been done with other simulation techniques, and of course, far more than what you can do on a QPU. So a good illustrative example of how you can use simulation to really do novel research, develop new algorithms, and validate them at scale. And we expect this all to get even better with Grace Hopper. So Grace Hopper combines Hopper with a CPU with a very large amount of memory. This is great for quantum computing simulation because the scale of what you can do is often limited by the memory, trying to fit a vector of size 2 to the n in classical memory for an n-qubit system. And so with Grace Hopper, this gets much more efficient, and the cost to simulate very large circuits goes down dramatically, up to an 87% reduction in the classical computational resources needed. So we really expect this to be another difference maker for quantum circuit simulation. All right, so switching gears from simulation to hybrid quantum classical computing. So in addition to helping us research and develop quantum algorithms, we expect classical supercomputers, GPU supercomputers, to actually couple two quantum computers and work together on useful applications. There are many things that quantum computers will never do well, and so this is going to be the future of useful quantum computing. This is going to take some work to realize. Quantum computers today are typically programmed in the equivalent of assembly code. This is great for for early experimentation, and of course there have been great results achieved already. But it doesn't translate well to integrating with a classical supercomputer and really kind of realizing useful quantum computing without bottlenecks. And there's actually kind of a good analogy to the early state of GPUs for scientific computing, where you program GPUs in assembly code or by hacking programmable shader APIs, but it wasn't so easy for non-experts to seamlessly leverage GPUs. And with the release of CUDA, we made it possible for you to program GPUs in C alongside your CPUs without having to be a deep domain expert, and that kind of ushered in a revolution in being able to utilize a new computing technology. So we see the same opportunity to open up quantum computing to a much broader group of domain scientists and make it possible for everyone to get all the benefits of GPUs, CPUs, and QPUs together. So with that in mind, we actually announced CUDA Quantum last year here at Q2B. It's now released open source, available on GitHub, and we also offer a Docker container on our container registry, NGC. It extends C++ and Python with quantum kernels, which can be compiled down to run on any quantum resource, either a simulated QPU or any type of physical QPU. It's hardware agnostic. In addition to being interoperable with different types of quantum processor, it's also interoperable with the best tools for classical computing and classical supercomputing, so CUDA and everything based on it, programming models like C++ standard parallelism, OpenMP, and OpenACC, and so it gives researchers and developers kind of the full suite of quantum, HPC, and AI tools at their disposal for developing new applications. As with our broader kind of platform goals, it's very important to us to partner broadly with CUDA Quantum, and we have a long list of partners now. And I want to highlight the 12 groups at the top, which represent quantum processors and different types of quantum processor. So as everyone in this room knows, there are many different quantum architectures, all have their strengths and weaknesses. Our aim at NVIDIA is to provide researchers with the ability to seamlessly run on any of them. So we're working with all these groups to connect CUDA Quantum to their processors and support the programming model for their processors as a first-class citizen in CUDA Quantum. We're also working with a growing number of groups building quantum software and applications, enterprise end users, and research centers. So, in addition to the interoperability benefits, we also see a great performance benefit from using CUDA Quantum. So this benchmark is a single iteration of VQE, where we're comparing code written and compiled in CUDA Quantum, simulated on a single A100 GPU, to code written and compiled in a leading Pythonic framework, also simulated on A100 GPU. So this is not a GPU to CPU speedup. The hardware is the same. These numbers are all the effect of software. And even at 20 qubits, we see CUDA Quantum is about, or almost 300 times faster, obviously with a very nice trend as the system is scaling. So we hope there will be great benefits to the community in terms of kind of interoperability, accessibility, as well as performance. And we're also making fast progress integrating CUDA Quantum with real quantum processors. So this example is, again, the variational quantum eigensolver, where on the left, we're running with a Q-quantum accelerated simulator, simulating what it would be to run this with perfect qubits. And on the right, we're running the same code on Quantinuum's H1 processor. So you'll notice that all you need to do to switch between running on the simulator and running on the QPU is this QPU compiler flag. So no code changes needed. We think this will be a nice workflow for people who want to do all of their development and simulation, testing and simulation, and then switch to the quantum processor for the final runs. And we have an exciting new announcement today, which is a new release of CUDA Quantum as well, CUDA Quantum 0.4. It features a number of new quantum processor connections, the Quantinuum one I just showed, as well as IonQ and Oxford quantum circuits, a new built-in quantum chemistry package with an integration with PySCF, support for MPI, PIP packaging, and much more. So please check that out today on NGC or on GitHub. Okay, so in the last part of the talk, I want to also talk about hybrid quantum classical computing and what's going to be required, but this time from the systems perspective. A programming model is important, but we also need to think about how we're going to physically tightly couple quantum and classical processors. And the reason is that high-performance computing is needed to get the most out of quantum computing and make quantum computing work. So a recent blog from Microsoft estimated petascale classical compute needed for fault-tolerant quantum computing because the requirements for error correction decoding are so huge. If you're not familiar, error correction decoding is something that has to be done classically. It has to be done much faster than the coherence time of the qubits. So we need lots of classical accelerated computing, and we need it coupled to the quantum processor with very low latency in order to enable fault-tolerant quantum computing. We also need accelerated computing for calibration of quantum systems, real-time optimal control, and for aforementioned hybrid algorithms. So with that in mind, a few months ago, we announced DGX Quantum. And so this is our system for enabling low latency hybrid quantum classical computing. It's in partnership with Quantum Machines and consists of 2 Grace Hopper superchips tightly coupled to the Quantum Machines OPX Plus control system. DGX Quantum is, I would say, the first system that really tightly integrates quantum with GPU supercomputing. It is qubit agnostic, and it dramatically reduces the latency to do hybrid GPU-QPU processing. It's also scalable, so I'll talk about that a little bit later, but you can go from very small quantum processors to thousands of qubits or more, and also scale with your classical requirements. Right, so we expect most groups are going to want to start with small quantum processors. One DGX Quantum can control 4 to 8 qubits. And as your systems scale up to 100 or 1,000 qubits, you can scale DGX Quantum with that by adding more OPX and more Grace Hopper. DGX Quantum also provides the interface to a full classical supercomputer for hybrid processing, because the Grace Hopper nodes can be connected over many of our interconnect technologies to a full supercomputer. And Grace Hopper is going to provide tremendous benefits for this as well, this time in terms of the latency to actually process data with the GPU. So most quantum processors today are accessed remotely through a web API. Of course, it's perfectly fine for experimentation, but the latencies involved are 1 to 10 seconds. So it's prohibitively slow for doing anything hybrid, let alone quantum error correction. For quantum error correction, it depends on the type of QPU, but in general, we need to do it much faster than the coherence time of the qubits. In superconducting qubits, this comes out to needing to do it in about 10 microseconds or less. So even connecting to the QPU via Ethernet is not really a viable solution. DGX Quantum uses PCIe and uses a low latency interconnect of the Grace Hopper superchip to be able to get data onto the GPU in less than 500 nanoseconds. And so this leaves plenty of time for compute on the GPU, and it's really the first system that enables using the GPU for this kind of application with low enough latency to really enable it to accelerate decoding. All right, so our platform, we aim to kind of provide a full suite of tools to accelerate quantum computing research, all the way from simulation to enable R&D for new quantum algorithms, a programming model to enable the integration of quantum into scientific computing and AI applications, and a system to enable us to get the most out of quantum computing accelerate quantum error correction decoding, and realize fault-tolerant quantum computing. So thank you all for your attention.